In this video, we're going to look at creating a graph of a function based off of the graph of its derivatives. We've done a little bit of work going forward, taking the function and creating the derivative graph from that. So we're going to start there just to formalize what we've been talking about, and that'll help us then work backward from the derivative graphs. So looking at this function, I'm not going to give you the equation for it. That's not necessary. What we want to look at are some of the patterns. And we were starting to notice some things before, and we're going to just bring that all together now. So first of all, I can see that on this first section of the graph, I can see that the slopes are all positive, and those slopes start out steep and get less steep until we reach this maximum value, and there we know the slope is 0. So what we can say right now then is that this slope is positive but decreasing. Positive slope, decreasing slope. They started out as positive numbers, but they're getting smaller and smaller, getting closer and closer to 0. And what we can say then about this function is that this function is increasing on this section. From left to right along the x-axis, the function is going up. So the function is increasing. Okay, let's look at the next section then. We have a slope of 0 at that maximum. Let's write that one down too, that's important. Slope equals 0, maximum. This is what's called a relative maximum. Let's use some more descriptive terms. This is what's called a relative maximum. It's relative because it's a peak. It's a peak on the graph. So it's a relative maximum, a turning point, if you will. Okay, let's look at the slope now for the next section. I can see that on this next section, the slopes are negative. So we have negative slope. And I can see that on this section, the slopes are still decreasing because we went from 0 and the slopes continue to decrease to negative numbers. So we've got a 0 slope and then a not very negative slope to a more negative slope to a more negative slope to a bigger negative slope. So I can say that these slopes are still decreasing, a decreasing slope here. But then something changes. How about, I don't know, I would say probably like right in here. The slopes start to change just a little bit there. The slopes are still negative. We can agree with that. Oops. The slopes are still negative. However, the slopes are getting less and less steep. So they start out as negative slopes, pretty big negative slopes, and the slopes become less and less negative. Let me put some lines on it. So we've got negative slopes. All of these are negative slopes, but these negative slopes are starting to approach 0 right here. So even though those are negative slopes, those slopes are starting to increase in value. So going from less negative to, or more negative to less negative, from more negative to closer to 0. So these slopes are increasing. And on this entire interval, where the slopes were all negative slopes, we know that the function is decreasing on this interval. Okay, then we can look at where the slope is 0 down here. We can say here that this slope is equal to 0, and that gives us a relative minimum. I can see that's a low point on the graph. It's a turning point, that's a low point on the graph. Okay, let's look at the slopes again. So if I draw the little tangent lines, the slopes then change back to being positive slopes. But as you can see, those slopes are still increasing. So we can say that we have a positive slope here. But the slopes went from 0 to being positive and then more positive and bigger positive numbers. So these slopes are increasing. And what we can see from this graph, the slopes are positive. So on this graph, on this interval, we can see that the function is increasing. So this is kind of a mess. We wrote all over this graph, and it's not really the most efficient way to do this. So I'm going to show you something right now. It's called a sign chart. And the sign chart is basically just taking this graph, along the x-axis, and describing the function based off of what we're seeing. So I'm going to shrink this down a little bit, that way we can see the function still. And I've drawn I've drawn a sign chart, and I'm going to put in some values that we know. So first of all, since this line is going to represent the x-axis, I'm going to say that we're going to start out here at negative infinity, and we're going to look at what's happening all the way to positive infinity along the x-axis. I'm going to write my infinity just a little bit better. Okay, so along this x-axis that I'm drawing here, so I'm just taking the x-axis from the graph above and putting it in this little sign chart. I am going to put some key points, some things where stuff changes. So what I'm going to do is look at, first of all, where the slopes are changing. So that's kind of important. We go from a positive slope to a negative slope, and that change happens at -3. The first change happens at -3. The next thing, oops, I missed it by a little bit. The next change that happens is that the slope changes from decreasing slope to an increasing slope at about 1/2, approximately. We'll talk about how to get that more precise later, but for now we're going to say about 1/2. And then the slopes change again from a negative slope to a positive slope at x = 4. So we're going to put those values, those are key points on the graph where things are starting to change. Okay, so now let's start to analyze some values here. From negative infinity to -3, we said that the slope of that graph was positive. So I'm going to say that f prime of x is positive from negative infinity to -3. And then from -3 all the way to 4, the slopes are negative. So I'm going to say from -3 all the way until 4, the slopes are negative. And then at 4, the slope changes to be a positive slope. So I'm going to say that from 4 to infinity, the slope is positive. And how that translates on the function is that the function is increasing here, decreasing here, decreasing here, and increasing. Okay, let's talk about how the slopes are changing. So you can see from negative infinity to -3, we see that the slopes are decreasing. They're going from very large positive numbers to 0. So that means the slope of the slope, so the second derivative, will be negative because those first derivatives, if we were to draw the first derivative graph, this first derivative graph would be decreasing on that first part, which means that the second derivative is negative there. If we look from -3 to 1/2, the slopes are still decreasing. So from -3 to 1/2, the slope of the slope is negative. Then things change. At about 1/2, the slopes start to increase. So that means the second derivative will be positive. The slopes continue to increase from 4 to infinity. They go from a 0 slope to a more and more positive slope. The slopes are still increasing, which means the second derivative is still positive. Now we haven't talked a lot about what that means on the graph. I can see that on this entire region where the slopes are decreasing, I want to get a highlighter. On this entire region where the slopes are decreasing, we have this part of the function. The slopes are decreasing right here. And so what we call that is this, we say that the graph is concave down on that interval. Concave down, it's like a parabola opening downward. So we know that on that region, this graph is concave down. And we can see that's true because the slopes are decreasing on that entire interval. So that makes the graph concave down. The second derivative is negative on that entire interval. So the function is concave down. Okay, now let's look at the next section. On this section here, the slopes are all increasing. In other words, the second derivatives are all positive. So what that means is you can see that this graph is opening upward. I bet you can guess that we call that concave up. It's concave up because the slopes are increasing or because the second derivative is positive. So let's just add that to our little chart here. So we know then on this entire interval that the function is concave down on this interval, concave down on this interval, concave up here, and concave up on this interval. So the way we describe this graph is from negative infinity to negative 3. The function is increasing, but concave down. So that kind of gives us that curve that's pointed downward. Because you guys have been asking, how do we know which way to curve the graph? Does the graph curve up or down? So in this case, the function is concave down on that first region. So we curve the graph in a downward direction. And then the function starts to decrease, still concave down. So we curve the graph that way in a more concave down direction. Okay, then at negative 1 or at positive 1/2, the function is still decreasing but changes to a concave up. So we curve the function the other direction to point upward, or to like a cup, if you will. And then the function increases and is concave up. All right, so let's put some names on here. We know that at negative 3, the function was increasing and then decreasing. So we have a relative maximum. At 1/2, at this point, that's where the function changes from being concave down to concave up. We call this a point of inflection. And at 4, the graph changes from decreasing to increasing. We have a relative minimum. Okay, it's time to work backward. So let's see if we can use a derivative graph to determine the function, the original function, what that graph might look like. I'm going to stop this here and I'll create a new video. That way I'm doing this in smaller chunks. So see you in a few.